Welcome to Brain Vision.
In this problem, we're going to be taking a look at a polarizer and an analyzer set up like this, where there's unpolarized light coming through this way, and it strikes the polarizer followed by the analyzer, which is tilted at a transmission angle, theta equals 27 degrees relative to that polarizer. So we can say that the polarizer starts off at theta equals 0 degrees. And the problem is telling us that we can add additional analyzers all the way down, as many of them as we want. And each one is going to be oriented at a transmission angle. That's another 27 degrees. So this one would be 54 degrees. And then so on and so on, right? Each one, that's theta 1, theta 2, theta 3 is theta 2 plus 27 degrees. Over here, theta 4 is equal to theta 3 plus 27 degrees, and so on. As many analyzers as we want. And the question is, how many of those analyzers will we need following that same pattern in order to reduce the intensity of light that strikes the first analyzer by a factor of 100? So we have unpolarized light over here, hits the polarizer, then it comes through with some intensity. And that'll be our initial intensity. It's the polarized light that comes through the first polarizer. And we want the final, we'll call that SF, the final intensity, to be equal to 1/100th of what that initial intensity was. Well, we know that as polarized light travels through more and more polarizers, there's an equation we can use. This is called Malice's law. It's one that you'll see very frequently when dealing with polarizers. Malice's law says that the transmitted intensity is equal to the incident intensity times cosine squared of theta. That's the relative angle between the polarized light and the polarizer. So in the first case here, we would be looking at cosine squared of 27 degrees. And after it passes through that, reaches the next analyzer, theta is again 27 degrees. 27 degrees here, another 27 degrees. So really what's happening is we have Malice's law being applied over and over and over again with cosine squared theta of 27 degrees every single time. So if we want to think about it like this, we have this intensity equal to the initial intensity times cosine squared theta n number of times. So cosine squared to the power of n, and n is the number of analyzers that there are. Each time you add a new analyzer, you just add another factor of cosine squared theta to it. So let's see if we can use that now to figure out the final intensity that we want. Scroll down our page a little bit. So what we want is 1/100th of the initial intensity be equal to initial intensity times cosine squared theta to the n power. Well, I think we see that the initial intensity cancels out on both sides, and what we're looking for is 1/100th to be equal to cosine squared theta to the n power. Now we know that theta is always 27 degrees, so let's go ahead and plug that in. 1/100th equal to cosine squared 27 degrees to the n power. Now to solve for that exponent n, I'm going to go ahead and take the natural log of both sides. Natural log of 1 over 100 is equal to natural log of cosine squared 27 to the n. And the reason for doing that is that the natural log on the right side allows us to move the exponent down as a factor. So natural log 1 over 100 is equal to n times natural log of cosine squared of 27. So many parentheses there. And now we just simply need to divide in order to solve for n. N is equal to the natural log of 1 over 100 divided by the natural log of cosine squared 27. Plug that into your calculator, and you're going to get something like 19.95. So basically, if you want to get down to a factor of 1/100th the initial intensity you started with, you need to add 19.95 or 20 of these analyzers in order to decrease the intensity by that amount.